So that was a discussion about classical conserved charges. Let's see what happens when we move to quantized charges. So when we want to quantize our theory, what we do is that we take the charges and we replace all the fields, say phi and pi. So these are the classical fields. We replace them by their, so we replace the Fourier, the coefficients in phi and pi by creation and annihilation operators, such as A dagger A, B dagger B, etc. So we also impose, this goes hand in hand, canonical commutation relationships so by replacing the Poisson brackets by commutators divided by I, and also h bar, but we put h bar equals to 1 in this course. We also normal order our operators and thereby we subtract some infinite vacuum energy. So let's see how these things work in practice. So in a previous lecture, we found that the quantized Hamiltonian, so let's write it as H quantized, is given by the classical Hamiltonian, but we normal order it. So here's a normal ordered symbol. Let me remind you what normal ordering means. Normal ordering means that if you have a bunch of creation and annihilation operators, then we push the annihilation operators to the right. So if you do this, then we found in a previous lecture that the normal ordering is given by the normal order expression for the Hamiltonian is given by this. And here we are introducing a shorthand whereby dk tilde, what we mean is that d cubed of k divided by 2 pi cubed 2 of ek. This is what we define. From now on, we will be using this shorthand notation. So this is something we have derived in a previous lecture. So here what we're going to do, we're going to derive the expression for the momentum operator. So pi, where I goes from 1, 2, and 3, we're going to derive the quantized momentum operators, and they're given by the classical momentum operator, but normal ordered. So what is this? Let us figure this out. Remember, we just derived a minute ago the classical momentum operator is given by minus the integral of phi dot and the spatial derivative of phi integrated over all of space. Now recall that phi of x is the integral over k. Then we have a of k e to the power minus I kx plus a dagger of k e to the power plus I kx. And therefore, phi dot of x is going to be given by so the derivative with respect to time is going to bring down a factor of minus I ki from the first term. So that term, the rest of the term is going to be same as before. For the second term, this is going to give rise to a minus sign. Right. And so similarly, if I look at the spatial derivative of phi, we're going to get, sorry, that was the spatial derivative of phi. Sorry, my mistake. And then we're going to work out what the time derivative of phi is. So the time derivative of phi is going to bring down factor of the energy. So it's going to bring down minus I of E of K, and then we will have A of K e to the power minus I kx minus of A dagger of K e to the power plus I kx. So you might wonder, why is the sign in both places the same? Well, here what's happening is that we are taking we can look at it a bit more carefully. Let's just work on the first term. So the first term is going to be, the spatial derivative acting on e to the power minus I kx. What is e to the power minus I kx? So first of all, the derivative is just this thing. And then we have e to the power minus I, e of k of t, and then we have plus I, k upstairs I, x upstairs I, and therefore we get I of k upstairs I times e to the power minus I kx, but this is nothing but minus I of k downstairs I e to the power minus I kx. So this explains the sign in front of the ki. So now that we have the expression for phi I and ki, we can then compute what minus normal ordering of the integral of phi dot and del I phi is going to be. So we integrate this over all space, and so we get three integrals. So we get an integral over, say, k1, an integral over k2, integral over all of space, and then we have minus e of k1, k of ki of 2, and then inside the bracket, we get four terms. One is a of k1, a of k2, e to the power minus I, k1 plus k2 of x, and then we get a term which is going to be a dagger of k1, a dagger of k2, e to the power plus I, k1 plus k2 of x, and then we are going to get two more terms. Those terms will be minus a dagger of K2, a of K1. So we have normal ordered this term, e to the power I for vector K2 minus K1 dotted with X. And then we are going to have the last term, which will be minus a dagger K1, a of K2, e to the power I, K1 minus K2, X. Now what we do is that we do the d cubed x integral, and all this delta function, all these exponentials give rise to delta functions. So we get these guys remain, and then here we get in the first term we have minus e k1 k, sorry, this should be k I of 2, and then from the first two terms we are going to get the same kind of delta function. So let me just separate out the first two terms. So we have a of k1, a of k2, and the integral is over the 3 dimensions. So we're going to have a leftover of the energy part in the exponential. We're going to have I of e of k1 plus e of k2 times t. And then from the second term, we're going to have a dagger of k1, a dagger of k2 times e to the power plus I, e of k1 plus e of k2t, and the whole thing will be multiplied by 2 pi cubed times d cubed of k1 plus k2, the three-dimensional delta function. And then we're going to get from the second term, there's a minus sign we can factor out, and here we're going to have a dagger of k2, a of k1, e to the power I of e of k2 minus e of k1 times t, and then we're going to have plus a dagger of k1, a of k2, and then that'll be multiplying e to the power I of e of k1 minus e of k2 times t, and the whole thing is multiplied by 2 pi cubed delta cubed of k1 minus k2. And this is it. So we can close the bracket. So now we do either, well, let's just do the k2 integral. If we do the k2 integral, we can use the delta functions, and then this becomes an integral over just k1, and then we have from the first term we have minus e of k1. This remains unchanged, but the k2 now becomes k1, so we get minus k1i, and then we have a of k1 times a of minus of k1, because the delta function had a plus sign here, and then we have e to the power minus 2i e of k1t, and similarly we have a dagger of k1 a dagger of k1 e to the plus 2I e of k1t. So this is the first term. And the second term, it's going to add up. All these exponentials are going to drop out because, this will be equal to this, and there's a minus sign. This will be equal to this, and there's a minus sign. And, these two terms are exactly going to be the same. So in the second term, we're going to have minus k1I times 2 of a dagger of k1a of k1. Now, if you look at the first two terms, it's easy to see that the integrand is an odd function. So the integrand is, this thing is nothing but some function of k1, and this function is k1I divided by e of k1, and then inside we have a of k1, a of minus of k1, so there should be a minus sign here, and then we have e to the power plus 2I e of k1 of t, then a of a dagger plus of a dagger of k1, a dagger of minus k1, and then we have e to the power minus twice I e of k1 of t. Now, e of k1 is nothing but this positive square root of k1 mod squared plus m squared. So this is an even function of k1. So these are even functions of k1, these are even functions of k1. And this is an even function of k1, this is an even function of k1, but this is an odd function of k1. And therefore, if I replace k1 by minus k1, we are going to pick up a minus sign. And therefore, the integrand of this first two integral is odd, and therefore, they are going to be integrating to 0 because our limit is from minus infinity to plus infinity. So as a result, only this term survives, and we can write the final result as our pi quantum is going to be given by d cubed of k. Now I'm writing out the measure explicitly, and 2 pi cubed 2 of e of k times the eigenvalue ki and the number operator of momentum k. So this is the expression for the quantum expression for the conserved momentum.